Imagine that I was able to gather energy together into one place. Like I could concentrate it into little clumps, the way that you might sweep dust into little piles on the floor, like this. Okay, well, that concentration of energy isn't going to last for very long because of the second law of thermodynamics. Energy spreads out. But let's just pause it for a minute and take a look. If we were to go to the center of the concentration, we'd see that the concentration of energy is still fairly high. But the further away you get from the center, the lower the concentration. That's because energy takes time to spread out. So what we have here could be described as a gradient, in which there is a gradual change through space in the energy level at any particular point. All right, go ahead and spread out. So if I wanted to have a permanent concentration of energy, some sort of fixture that won't just disappear and spread out, well, I'm going to run into problems with the second law of thermodynamics. I could have a dynamic equilibrium set up where I'm continually reconcentrating it at the same rate that it's spreading out, but that would take a lot of work. If only there was another way to have a permanent fixture that could be a source or concentration of energy. Well, actually, that's kind of what a particle is. Different kinds of particles interact with different kinds of energy. Now, we're talking about the electric field. In other words, the description of how much electrical energy is in every point in space. So we need to have a particle that has electrical energy, or at least interacts with electrical energy. I think an electron would be a good choice. So let's just stick an electron here. And then take a look at the level of electrical energy at every point in space around it. We're basically looking at the electric field of an electron. So if we look right here at the electron, the concentration of energy is, well, it's the highest. That's where the electron is. So let's move away from it just a little bit. The amount of energy here is still high, but it's lower. The further away you go, the lower it is. Because this is expanding into three-dimensional space, the concentration of energy is decreasing proportionally to the square of the distance. That's our inverse square law. Okay, so we're looking at an energy gradient here, because as you move away from the source of the energy, remember when I say source, I mean the locus, the concentration of it. It's not like it's producing any, it just possesses it. And the closer you get to the electron, the higher the level of electrical energy you encounter. Okay? You could almost imagine it's like the top of an electrical hill. Or, since it's negative, maybe the bottom of an electrical pit. Anyway, the closer you get to that source, the higher the magnitude of the energy that you'll encounter. Because you're moving through a gradual change in an energy level, we call that a gradient. Now, going back to our hill or pit metaphor, if you wanted to have a map of a landscape, you could have a map that shows lines that indicate levels of equivalent height or elevation. These are topographical maps, and you can use these to navigate a hiking trail or just to get an idea for the topography of some landscape. But what if you were to draw lines that follow paths in which the electrical field is changing in a predictable fashion? That is what you're looking at when you look at a map of an electrical field with lines on it, when you're looking at electric field lines. These electric field lines are just the path along which the electric energy is decreasing according to that inverse square law in that predictable mathematical fashion. So if you see a more complicated map, well, map kind of is an apt word. I mean, we're looking at the landscape of space and we're selecting a particular aspect of space to look at, kind of like you could choose a satellite map, or you might choose a map that shows you borders and town names and road names. If you look at a map of space and elect to see the concentration or level of energy of the electric field, you're just looking at electric field lines. And if you look at a more complicated map, you're just looking at a varied landscape full of hills and valleys.